Hello, everyone, and welcome to Armagh Astrobytes, a series where we take astronomy and break it down into bite-sized chunks. We're joined again today with Professor Michael Burton, who's the director of Armagh Observatory and Planetarium, and today we're going to discuss cosmology. So, Michael, this is a truly grand topic. So, how have astronomers realised that they can study the history of the universe itself?
Indeed, this is a massive topic. And I'm going to try and explain that by talking about this rather complicated looking diagram. But this picture here goes back about 100 years ago to the days of Edwin Hubble. And what we see in this picture is, on the left, we see a picture of a series of galaxies, large galaxies at the top, smaller galaxies down the bottom. And on the right, we see what are called spectra, which is spreading the light out from those galaxies, a bit like going through a rainbow and seeing what that light is made up of. And this particular data set, originally taken by Edwin Hubble, actually allows us to probe back to the history of the universe itself. And let me try and explain that. So let's start by looking at the left-hand side. The left-hand side, these are these elliptical galaxies we've been talking about in previous Astrobytes. And these actually galaxies are the largest galaxies in different clusters of galaxies. So what Hubble did was he made the assumption that each one of these galaxies is actually the same size, but the different angular size we see in the sky is directly related to how far away it are. Basically, the smallest ones are furthest away, the largest ones are closest. So he had a relationship between angular size and distance. What he also did was he measured the spectra, and that's what's shown on the right. And so he spread the light out. It's a bit like going through a prism. The light's being spread out here. And he's taken a couple of little lines. They come from the element calcium. The technical name is the H and K line, but the name doesn't really matter. You can see these two little absorption features here. See these dark lines here. We see it again here. We see it again here, and here, and here. And basically, he's measuring the wavelength where these calcium features come. And what he's finding is that the wavelength gets longer and longer the further and further away it is. Basically, you can measure the speed of the recession. It's through what's called the Doppler effect. You can measure the speed and you can measure the distance. And that's what Hubble did.
So what did Hubble find?
Well, what Hubble found is shown in this picture here. This is actually a modern version of Hubble's diagram. This is plotted the distance to the galaxy. That's really the angular size as estimated by those images. And on the y-axis, we see the speed the galaxy is moving. This is measured from the Doppler shift. And what Hubble found was there's a relationship, a clear relationship. The further a galaxy was away from us, the faster it was moving away from us. Now, in fact, Hubble wasn't the only person who contributed to this result. There was actually a Belgian astronomer, Georges Lemaître, who actually came up with a very similar result, actually slightly before Hubble. And recently, a couple of years ago, the International Astronomical Union recognized that by renaming the Hubble law, the Hubble-Lemaître law, in honor of these two people who contributed to this very important diagram, which tells us about the nature of the universe we live in.
That's amazing. It's so good that they actually did that. But what does the result actually mean from this?
So that's what this next diagram is trying to explain. So what they found was that everything seems to be moving away from us. Not only that, the further away you are, the faster it is. So there's two possibilities for that. One is we are the center of the universe and literally everything is moving away from us. But since the time of Copernicus, scientists have moved away from that kind of conception. When Copernicus day, we had the Earth, the center of the universe, and Copernicus put the sun the center, essentially the heliocentric hypothesis. Well, since astronomers don't believe that we truly are the center of creation, they have an alternative explanation, and it's summarized in this diagram here. The way to think about this is, and this is an analogy because you really have to work in four-dimensional space to understand it properly. Let's suppose all the galaxies are lying on the surface of a balloon. So these little stickers, these little coins are stuck on a balloon, and then you're blowing the balloon up. And as you blow the balloon up, if you take any one of these galaxies, you will find, so galaxy here, you'll find that galaxy over here, all the neighboring galaxies are getting further and further away from it. And basically take any galaxy on this rubber balloon, and every other galaxy will be moving away from you. So that's our current picture, is that essentially the entire universe itself is expanding, but rather than being a two-dimensional surface expanding into a three-dimensional space, we're really in a three-dimensional surface expanding into a four-dimensional space.
Wow. Okay, so Hubble made these measurements about 1 century ago. As telescopes that we have now get better and they're able to look further into the cosmos, have we been able to test out these conclusions further?
Yes, we have, and we've tested them out and we found they're not quite right. Things have actually changed. So let me explain how it is that, that we can do that. So we need to find some way of measuring the distance. That's the most challenging part. And we use what are called standard candles. Standard candles are objects which have a known brightness, and then the relative magnitude that we see can be related to how far away it is. And the best standard candle we found are these supernova. We heard about supernova earlier in the Astrobytes. These are when a star explodes and can be as bright as an entire galaxy for a few days. And particular kinds of supernova essentially all look the same. So essentially by measuring these supernova, we're able to probe further and further into the universe and try and understand its history more and more.
So when we do this, do we find that the Hubble limiter still holds that the universe is linearly expanding?
We do for parts of it, but in fact, in the most recent part of the time, we're finding that law is not quite right. In fact, not only the universe still expanding, but the expansion is actually accelerating. And that's what this sketch here is trying to illustrate. This is not data, this is the sketch. We're right here, we're a telescope looking back in time. As we go to the left-hand side, we're looking back in time towards the origin of the universe. And the width of the diagram essentially represents the size of the universe over time. So this cone here, which has got a kind of a straight line linear form over this part, is the Hubble expansion. But in fact, you can see in recent times, actually, it's accelerating. It's getting larger and larger, more and more rapidly. So this is what we now interpret as the acceleration of the expansion of the universe. But the other part of this diagram is that as we look back in time, the galaxies of today, we see the building blocks of the galaxies are going back billions of years ago. And we go back to a time before the first galaxies actually formed. And in fact, a time when the universe was only full of gas. And in fact, we can peer back as far as a time only shortly after the Big Bang, where there's a radiation coming out from the radio called the cosmic microwave background.
So what is this cosmic microwave background?
So I'm showing a modern view, the best picture we have now of the background measured by a European Space Agency satellite called the Planck satellite. This is a discovery which goes back about 50 years ago, just over 50 years ago. And essentially, if you turn a radio on and don't have it tuned to a radio station, you can hear a background hiss. That hiss, in fact, much of it is actually coming from the universe itself. It's a kind of cosmic static. We now know that this arises from a time about 400,000 years after the Big Bang, in fact 380,000 to be precise, when the first atoms formed. The electrons and protons came together to form the first atoms, and at that point radiation could travel unimpeded through the universe. And essentially we're seeing photons going back to this time shortly after the formation of the universe itself, which has been traveling in a straight line ever since. When they were first released, they were much, much hotter, maybe at a temperature of several thousand degrees. But in that expansion over the last 14 billion years, they've cooled down. And in fact, this radiation is now at a temperature of only 2.7 degrees above absolute zero. But in fact, this diagram here shows more than that. It's not just showing you the distribution at that temperature, it's showing the fluctuations in that temperature. And the difference between the red and the blue in this diagram are tiny, tiny temperature fluctuations of about 0.003 of a degree, which we can accurately measure in the background. And we now realize that these essentially are like ripples in time. These little slightly hotter and slightly cooler regions actually provided the seeds from which galaxy clusters formed, and ultimately the galaxies in today's universe came from these seeds.
So what is our current understanding of how the universe actually began?
So we have another little schematic here to try and put all this, essentially 14 billion years of evolution of our universe in one diagram. So here we are today, modern universe full of galaxies around us, and we can peer back, and in the radio part of the spectrum, in fact, it's the microwave part of the spectrum, we can see this cosmic microwave background where these sort of slight temperature fluctuations led to the formation of the galaxies we have today. But these temperature fluctuations must have come from an even earlier phase in the universe. In the first fraction of a second of the universe, fluctuations, quantum fluctuations, we so-called, essentially the random changes which quantum mechanics lead to. You can't have a perfectly smooth universe. And those quantum fluctuations themselves must have arisen from what we call a Big Bang, the dawn of time, an event we still cannot understand because it actually goes beyond our current understanding of physics.
So what does all this mean for our universe?
So let me try and wrap up what we do understand and some of what we don't understand in this final slide. So essentially peering back through time, seeing the cosmic microwave background, seeing the expansion of the universe allows us to estimate an age of the universe. And we're fairly confident we do know how old the universe is. It's about 13.8 billion years, about 3 times the age of our sun, in fact. We think the universe will expand forever. In fact, our best understanding is it's accelerating, and in fact, the universe is going to get further and further apart, all the stars and galaxies, eventually in zillions of years into the future. But there's many, many things we don't understand. And what I want to highlight here is our current understanding, in fact, lack of understanding about what the universe consists of. So this diagram essentially relates to 3 components of the universe. Only one part of that component, this yellow section here, what I call ordinary matter, is what we actually understand. Ordinary matter is stuff like us, like planets, like stars, things we can see, things we can feel, things we can measure. But in fact, much of the universe we can't see, we can't even feel it at times. So this next sector over here, this blue one here, which covers about 1/4 of the universe, we call that dark matter. So when we look at distant galaxies, we can see those galaxies rotate. But if we try and work out how much matter there is, based upon how fast they're rotating, we find that the mass of the galaxy is actually a lot more than the amount of matter we can see, which is the visible light that's coming from us. So we call that dark matter. It's stuff we can feel, but we can't see. And we believe it forms about 1/4 of stuff our universe is made up of. But in fact, the biggest part of the universe is something we really have absolutely no idea about. We call it dark energy. And this is what's leading to this cosmic repulsion. This is the expansion, in fact, the acceleration of the universe, driving the universe apart faster and faster. But we really don't understand it. It's the biggest mystery in the cosmos today.
Wow, so there's obviously plenty more to understand and to investigate. So for everyone at home, this is actually the last Armagh Astrobytes in the series. Over the past 3 months, we've journeyed from our solar system, through the stars of our galaxy, then to the realm of galaxies, and then to the birth of the universe itself with the Big Bang. We hope you have enjoyed it and have learned a lot about astronomy along the way. But also, there's a lot more to be discovered, obviously, and many mysteries to be explained. So this is just goodbye for now.
Goodbye.